Welcome. Take a deep breath and settle in. Let your mind slow down as we explore a strange and fascinating puzzle. Paradoxes are ideas that don't fit neatly into the rules of logic. They twist and turn, making us question things we thought we understood. Tonight, we begin with one of the most famous paradoxes in history, the liar paradox. Imagine someone looks at you and says, "I am lying." On the surface, it seems like a simple statement, but let's think about it carefully. If the person is telling the truth, then their statement must be accurate. They are lying. But if they are lying, then what they said wasn't true. That means they are actually telling the truth. But if they are telling the truth, then they must be lying. No matter how you approach it, the statement keeps contradicting itself. If it's true, it must be false. If it's false, it must be true. It's like an endless loop, a logical trap that refuses to resolve. This paradox was first recorded by the ancient Greek philosopher Eubulides over 2,000 years ago. Since then, it has fascinated thinkers across generations. Philosophers, logicians, and mathematicians have all wrestled with its meaning. It may seem like a simple trick of words, but it raises a much deeper question. What does it really mean for something to be true? We like to think that statements are either true or false, but the liar paradox challenges that idea. It forces us to consider the possibility that truth and falsehood might not always be as clear-cut as we assume. In the 20th century, mathematician Kurt Gödel used a similar idea to prove something incredible. He showed that in any logical system, there will always be statements that cannot be proven to be either true or false. His discovery reshaped mathematics and showed that even the most precise systems have their limits. The liar paradox also appears in everyday life. Imagine a headline that reads, "Everything in this newspaper is false." If the headline is true, then everything in the newspaper must be false, including the headline itself. If the headline is false, then at least some things in the newspaper must be true, which would make the headline true again. This paradox plays with the way we use language. It exposes the hidden assumptions we make about truth and meaning. It reminds us that not everything fits neatly into the categories we try to place them in. Let your mind rest on that thought, a sentence that is both true and false at the same time, a contradiction with no resolution. There is nothing to figure out, nothing to solve, just an idea drifting in and out of focus like waves rolling onto the shore. Now let's move on to the next paradox. A small town has a barber. He follows one strict rule. He shaves every man in town who does not shave himself, and he never shaves any man who does shave himself. Now here's the question. Who shaves the barber? If the barber does not shave himself, then he falls into the category of men who do not shave themselves. And according to his rule, he must shave those men. That means he must shave himself. But if he shaves himself, then he is now someone who shaves himself, which means he should not be shaving himself at all. On the other hand, if he chooses not to shave himself, then by his rule, he must shave himself. If he does shave himself, then he should not. If he does not shave himself, then he must. The logic falls apart. At first it seems like a simple question, but there is no answer that makes sense. No matter how you look at it, the barber's rule creates a contradiction that cannot be resolved. He must shave himself, but at the same time, he must not. This paradox was introduced by the mathematician Bertrand Russell in the early 1900s. He used it to highlight a problem in logic. Some rules, when applied to themselves, lead to contradictions. If a system is too broad, it may collapse under its own weight. Russell's paradox was not just about barbers. It appeared in the foundations of mathematics itself. He discovered that certain sets, like the set of all sets that do not contain themselves, created logical contradictions, just like the Barber paradox. A set must either contain itself or not, but in some cases, neither option made sense. This discovery forced mathematicians to rethink the way logic and mathematical systems worked. But the Barber paradox also has meaning outside of math. Sometimes, rules that seem clear at first can break down when applied to themselves. Laws, systems, and even ideas we take for granted can sometimes create contradictions that make them impossible to follow. Think about rules that apply to themselves in daily life. Imagine a library that says, all books that do not reference themselves must be listed in this catalogue. Should the catalogue itself be included in that list? If it does reference itself, it shouldn't be there. But if it doesn't reference itself, then it belongs in the catalogue, which would then make it reference itself. Just like the barber, it leads to an unsolvable contradiction. Even language itself can create problems like this. If a sign says, ignore this sign, what should you do? If you ignore it, then you are following what it says. But if you follow what it says, then you are not actually ignoring it. The Barber paradox is a reminder that logic does not always work as neatly as we expect. It shows that some rules break down when turned inward, leading to conclusions that cannot be true or false. The Sorites paradox. Imagine a pile of sand, a true heap made up of thousands of tiny grains stacked together. If you remove one grain, does it stop being a heap? Of course not. It still looks the same. Now remove another, and another. It's still a heap. The change is so small that it barely matters. But if you keep going, at some point, the heap is gone. You're left with just a single grain of sand. The question is, when did it stop being a heap? Was it when there were 100 grains left? 50? 10? Or was there no exact point at all? This is the Sorites paradox, sometimes called the paradox of the heap. It shows up whenever we try to define something with vague boundaries. A heap isn't a precise number. It's an idea, something we recognize without strict rules. This paradox isn't just about sand. It applies to almost anything that changes gradually. Take a person's hair. If someone starts losing hair one strand at a time, at what point do they become bald? If you remove just one, they aren't bald. Remove another and another. No single hair makes a difference. Yet at some point, the person is undeniably bald. Or consider aging. A child grows into an adult so slowly that there's no single moment when they become one. Every day they change slightly, just like the heap of sand. Yet at some point we look at them and say, they are no longer a child. But when exactly did that happen? This paradox creates problems in law and ethics as well. Think about wealth. If you slowly give someone a penny at a time, they are not suddenly rich because of one coin. But at some point, they will have enough money that we consider them wealthy. The same goes for poverty. No single dollar taken away makes a person poor, but take away enough, and eventually they are. The problem with the Sorites paradox is that it reveals how difficult it is to draw a clear line when things change gradually. Words like heap, bald, young, or rich are not precise. They rely on our perception rather than strict definitions. Philosophers have debated this paradox for centuries. Some argue that vague concepts are simply unavoidable. Others suggest that everything must have an exact cut-off point, even if we don't know what it is. But no matter how we approach it, the paradox remains. It forces us to question how we define things and whether any concept with vague boundaries can ever be perfectly understood. Zeno's paradox. Imagine standing a short distance away from a wall. You take a step forward, but before you reach it, you must first travel halfway. After that, you must go half of the remaining distance, then half of that, and half again. If you keep cutting the distance in half, it seems like you will always have more ground to cover. No matter how small the gap gets, there is always another halfway point. If this logic holds, movement itself should be impossible. This is Zeno's paradox, first proposed by the Greek philosopher Zeno of Elea over 2,000 years ago. He used it to argue that motion is an illusion, something that cannot logically exist. But clearly we move every day. So where does the paradox go wrong? At first, it seems like common sense should solve the problem. If you keep stepping forward, no matter how many times you divide the distance, you will eventually reach the wall. But mathematically, Zeno's argument is tricky. The sum of an infinite number of small distances still adds up to a finite amount. In reality, you do reach the wall, but the paradox shows how our intuition struggles with infinity. A similar version of this paradox involves a runner trying to reach the finish line. Before they can reach the end, they must first cover half the distance, then half of what's left, and so on. If this logic were correct, no runner would ever finish a race, since they would always have another fraction of the distance to go. Yet races end all the time. Mathematicians later solved this paradox using calculus. They showed that even though the steps are infinite, the total distance remains finite. That's why, in the real world, we do reach the wall. But Zeno's argument highlights something strange about the way we think about infinity. When we break things into smaller and smaller parts, they can seem endless, even when they aren't. This paradox also appears in physics. When scientists study motion at a microscopic level, they find that things don't move smoothly. Instead, particles jump between positions in ways that don't always match our everyday experience. Some theories even suggest that space itself is not infinitely divisible, meaning Zeno's paradox might not just be a thought experiment. It could reveal something deeper about reality. At its core, this paradox is about how we understand movement, space, and infinity. It shows that even something as simple as walking can lead to questions that are not so easy to answer. The grandfather paradox. Imagine you discover a way to travel back in time. You set the machine, press a button, and suddenly you find yourself decades in the past. Everything looks different, yet familiar. The world is still in motion, following the course of history that led to your birth. But what if you changed something? What if you prevented your grandparents from ever meeting? If they never met, then your parents were never born. And if your parents were never born, then you were never born. But if you were never born, then how did you travel back in time in the first place? This is the grandfather paradox, one of the most famous time travel paradoxes. It creates a contradiction where your very existence depends on something that you erased. The moment you interfere, you erase the conditions that allowed you to interfere in the first place. At first, it seems like there must be a way out. Maybe history would correct itself. Maybe someone else would step in and take your grandfather's place. Some theories suggest that time protects itself, making sure that events unfold the way they always have. But what if they don't? What if your actions create an entirely new timeline? One possibility is that the universe splits into two. In one timeline, you were never born. In another, you still exist, but in a different reality. This is known as the many worlds interpretation. It suggests that every action, every decision, every possible outcome creates a new branch of reality. But if there is only one timeline, the paradox remains. Some have suggested that time travel to the past is simply impossible. Others argue that if you did go back, you would always fail to make major changes. Maybe you trip at the last second. Maybe a coincidence stops you. The past resists, preventing contradictions from happening. This paradox has fascinated physicists, philosophers, and storytellers alike. It raises questions about free will, destiny, and whether time is something that can be rewritten. If time travel were possible, would we truly have the power to change the past? Or would every attempt simply become part of the story that was always meant to happen? The bootstrap paradox. Imagine you discover a book filled with detailed instructions on how to build a time machine. You follow the steps, construct the machine, and travel back in time. While there, you give the book to a young scientist who studies it carefully and uses it to write the original version of the book. But here's the problem: who actually wrote it? This is the bootstrap paradox, a strange loop in time where an object, piece of information, or even a person has no clear point of origin. It exists because it was sent back in time, but it was only sent back because it already existed. One of the most famous examples is the Shakespeare paradox. Imagine you go back in time with a copy of Shakespeare's complete works. You hand them to Shakespeare before he ever wrote them. He copies them down, word for word, and history unfolds exactly as it always did. But if he never actually created the plays himself, where did they come from? The paradox gets even stranger when applied to objects. Suppose a scientist invents a time machine and decides to test it. He places an old, worn-out watch inside, sets the dial, and sends it back 100 years. A historian finds the watch, preserves it, and eventually it ends up in a museum. Decades later, the same scientist discovers it in the museum, takes it, and uses it for his experiment. The watch was never built, never created. It simply exists in an endless loop. This paradox raises serious questions about cause and effect. Normally, events follow a logical order. Something happens leading to the next event and so on. But in a bootstrap paradox, the sequence folds back on itself. There is no clear beginning. If information can be passed through time without ever being created, what does that say about knowledge? Could someone discover something they were never supposed to? Could you send a famous novel or scientific breakthrough into the past, allowing history to unfold exactly as expected? And if so, who actually created it? This paradox challenges our understanding of time itself. Does time have fixed rules, or can it bend in ways that make cause and effect meaningless? If the past and the future can influence each other in a loop, is anything ever truly original? The Ship of Theseus. Paradox. Imagine a great wooden ship, one that has sailed for many years. Over time, the planks begin to wear out. One by one, they are replaced with new ones. The sails are changed, the mast is repaired, and eventually, every single piece of wood has been swapped for a new one. Now here's the question: is it still the same ship? At first, it seems like the answer should be yes. After all, the ship has been continuously maintained, and it has never stopped being the Ship of Theseus. But if every single part has been replaced, what exactly makes it the same ship as before? Now imagine something else. Someone gathers all the old, worn-out pieces that were removed and assembles them into a second ship, one built entirely from the original parts. That ship looks exactly like the first one did before the repairs began. So which is the real Ship of Theseus? The one that has been slowly rebuilt piece by piece? Or the one that was reconstructed from the original materials? This paradox forces us to question what makes something the same over time. If every part of an object is changed, at what point does it stop being the thing it once was? The same question applies to people. The cells in your body are constantly regenerating. Every few years, almost all of them have been replaced. Your thoughts change. Your memories fade. Are you still the same person you were as a child? If not, at what point did you stop being that person? This paradox also applies to objects and identities in the real world. If a company slowly replaces every employee, every building, and every policy, is it still the same company? If a classic car has every single part swapped for a new one, is it still the same car? Some argue that identity is not tied to physical parts, but to continuity. As long as the ship has been in continuous use and recognized as the ship of Theseus, it remains the same. Others say that once every piece has been replaced, it is no longer the original ship, only a replica. But if that's true, then what about the ship built from the old parts? If we say that is the real ship of Theseus, then how can a ship that was completely disassembled and rebuilt still be considered the same? The paradox reveals how difficult it is to define what makes something truly the same over time. Whether it's a ship, a person, or an idea, everything changes, but at what point does it become something new? The omnipotence paradox. Imagine a being that is all-powerful. It has no limits, no weaknesses, and can do anything. Now consider this question. Can this being create a rock so heavy that even it cannot lift it? If the being can create the rock but cannot lift it, then it is not truly all-powerful because there is something it cannot do. But if it cannot create the rock in the first place, then there is still something it cannot do. Either way, the idea of unlimited power leads to a contradiction. This is the omnipotence paradox. It challenges the very idea of absolute power. If a being can do anything, then it should be able to create a rock it cannot lift. But if it cannot lift the rock, then it is not truly all-powerful. If it cannot create such a rock, then again, it has a limitation. Some have tried to resolve the paradox by redefining omnipotence. One argument is that an all-powerful being can do anything that is logically possible. Creating a rock so heavy that it cannot be lifted may simply be a meaningless request, like asking if a square can be a circle. In this view, omnipotence does not mean doing the impossible, just everything that can possibly be done. Others argue that true omnipotence should not have logical limitations. If a being is truly all-powerful, it should be able to make contradictions real, like making 1 + 1 = 3, or creating a triangle with 4 sides. But if contradictions can be true, then logic itself breaks down, making power meaningless. This paradox appears in philosophy, theology, and even discussions of artificial intelligence. If a super-intelligent AI could rewrite its own code, could it make itself so powerful that it loses control of itself? If so, would it still be intelligent? If not, is it truly unlimited? The omnipotence paradox is not just a question about gods or supreme beings. It is a question about limits, power, and whether there can ever be such a thing as true, unlimited ability. The unexpected hanging paradox. A judge tells a prisoner that they will be hanged at some point next week. The execution will come as a surprise. On the morning of the hanging, the prisoner will not see it coming. The prisoner thinks carefully. If the execution happens on Friday, then by Thursday night they will know it must happen the next day. But if they know it's coming, then it won't be a surprise. So Friday is impossible. Now they consider Thursday. If Friday is ruled out, then by Wednesday night, they will know the hanging must happen on Thursday. But if they know in advance, then it is not a surprise. So Thursday must also be impossible. Using the same logic, they rule out Wednesday, then Tuesday, then Monday. In the end, they convince themselves that the execution can never happen. But then, one morning, perhaps Wednesday, they are taken by surprise. The execution happens, and the judge's statement turns out to be true. This is the unexpected hanging paradox. It creates a contradiction between logic and reality. The prisoner's reasoning appears flawless, yet it leads to a false conclusion. At its core, this paradox challenges our understanding of knowledge and prediction. The prisoner assumes that if they can logically deduce the day of the hanging, it cannot happen. But this assumption itself leads them to an incorrect expectation, allowing the execution to remain a surprise. This paradox is not just about hangings. It applies to any event that must remain unpredictable. If someone tells you that a surprise test will happen next week, and you use the prisoner's logic to rule out every possible day, you might let your guard down, only to be caught off guard when the test actually happens. The paradox also raises questions about self-referential logic. The prisoner's reasoning seems sound, yet it fails because it assumes that logical deduction can override reality. But what if knowing something changes its outcome? If knowledge of the event affects whether it happens, can we ever truly predict the future? Hilbert's hotel paradox. Imagine a hotel with an infinite number of rooms. Every room is occupied. There are no empty spaces. A new guest arrives, hoping to check in. In an ordinary hotel, the manager would have to turn them away. But this is Hilbert's hotel, and here infinity works in strange ways. Instead of rejecting the guest, the manager has an idea. He asks each current guest to move one room over. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The process continues endlessly. Since there is no final room, this shift never runs out of space. Room 1 is now empty, and the new guest can check in. Even though the hotel was full, it somehow made room for more. Now, imagine that an infinite number of new guests arrive all at once. Again, it seems impossible to fit them all in. But the manager has another plan. Instead of moving everyone over by one room, he tells each guest to move to the room number that is double their current one. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Since there are infinite even-numbered rooms, every existing guest still has a place, and all the odd-numbered rooms are now free, ready for the infinite new arrivals. This is Hilbert's hotel paradox, a thought experiment created by mathematician David Hilbert to demonstrate the strange properties of infinity. In the real world, a full hotel cannot accept new guests, but in an infinite hotel, there is always a way to shift things around. This paradox highlights the difference between a large number and true infinity. No matter how full infinity seems, it is still able to grow. It also challenges the way we think about space, numbers, and limits. If you remove half of the guests, the hotel still has an infinite number of people inside. If you double the number of guests, it still remains infinite. Unlike anything in everyday life, infinity never runs out. This paradox has deep implications in mathematics and physics. In the universe, some theories suggest that space itself could be infinite. If that is true, then ideas like Hilbert's hotel might not be just a thought experiment. They could describe something real about the nature of existence. The Fermi paradox. The universe is vast. There are billions of stars in our galaxy alone, and beyond that, countless more in the observable universe. Many of these stars have planets, and among them, some should be capable of supporting life. If even a tiny fraction of these planets developed intelligent civilizations, the universe should be teeming with life. So where is everyone? This is the Fermi paradox. It asks why, despite the overwhelming number of opportunities for intelligent life to exist, we have seen no clear evidence of it. No signals, no spacecraft, no visitors. One possible explanation is that intelligent civilizations are extremely rare. Perhaps the conditions needed for life to emerge are far more precise than we realize. Maybe Earth is a unique exception, a rare accident in an otherwise lifeless universe. Another possibility is that life does emerge frequently, but rarely evolves into intelligent beings capable of communication. Dinosaurs ruled Earth for millions of years without developing technology. Intelligence, as we define it, may not be the inevitable path for life. Some theories suggest that civilizations destroy themselves before they can explore the universe. Whether through war, resource depletion, or environmental collapse, intelligent species might be prone to self-destruction before they reach a stage where they can make contact with others. Another explanation is that advanced civilizations are deliberately avoiding us. Maybe they exist but choose not to interact, treating Earth as an experiment or a protected area, much like a nature reserve where human interference is forbidden. There is also the possibility that we are simply looking in the wrong way. The universe is unimaginably large, and our current technology may be too primitive to detect alien signals. If extraterrestrials communicate using methods beyond our understanding, we may not even recognize their presence. Some have even suggested that we are alone, not because life is rare, but because we are the first. In this view, intelligent civilizations are just beginning to emerge across the universe, and we happen to be one of the first to develop. The Fermi paradox is unsettling because it suggests that something about our understanding of life and the universe is incomplete. Either intelligent life is much rarer than we assume, or something is preventing civilizations from reaching out to one another. The Monty Hall problem. Imagine you're a contestant on a game show. You're standing in front of 3 doors. Behind one door is a shiny new car, and behind the other 2 are goats. Your goal is simple. Pick the door with the car. You choose a door. Let's say door 1. Now the host, Monty Hall, who knows what's behind every door, opens door 3, revealing a goat. Monty then asks, "Would you like to switch your choice to door 2 or stick with door 1? Intuitively, it may seem like there's no reason to switch. After all, there are 2 doors left, and you might assume that the odds of getting the car are now 50-50. But surprisingly, your chances of winning the car are actually higher if you switch. When you first chose a door, you had a 1 in 3 chance of picking the car and a 2 in 3 chance of picking a goat. Monty's action of revealing a goat behind one of the other doors doesn't change the initial probabilities. The odds of the car being behind the door you initially picked remain 1 in 3. However, because Monty knows where the car is, he's always revealing a goat. So, when he offers you the chance to switch, your chances of winning by switching are actually 2 in 3. This is because if you initially chose a goat, which had a 2 in 3 chance of happening, switching will give you the car. If you initially chose the car, which only had a 1 in 3 chance, switching will give you a goat. The Monty Hall problem confounds our intuitions about probability. It's easy to think that once Monty reveals a goat, there are 2 remaining doors, each with an equal chance of hiding the car. But the key to the paradox is that Monty's actions have actually given you extra information, increasing your odds of winning if you switch. The lesson here is that our intuitions about probability are often wrong. Even when we think we're making the most logical choice, probabilities can work in ways that are difficult to grasp at first. The paradox of the unexpected exam. Imagine a teacher tells a class that they will have a surprise exam at some point during the next week. The exam will be unexpected. It will happen on a day that no one anticipates. The students are told that they should be prepared, but they won't know the day of the exam in advance. At first, the students think this seems fair enough. They know the exam will come before the end of the week, but they can't be sure on which day. However, as the week progresses, they begin to reason. If the exam hasn't happened by Thursday, then it must occur on Friday. But the teacher said it would be a surprise, so Friday can't be the day. If they know it's happening on Friday, then it wouldn't be a surprise. This reasoning leads them to eliminate Friday, and by the same logic, they eliminate Thursday. If the exam hasn't happened by Wednesday, it must happen on Thursday or Friday. But as they've already ruled out those days, they now eliminate Wednesday as well. By continuing this line of thought, the students eventually conclude that the exam cannot possibly take place at all. Since they can predict that it will never occur without being expected, they believe it's impossible. But then, on a random day earlier in the week, the teacher gives the exam. The students are surprised. Their reasoning, while seemingly logical, was completely wrong. This is the paradox of the unexpected exam. It's a situation where the very idea of surprise leads to a contradiction. The students' attempts to predict the exam create the conditions that make it impossible for them to predict it. The paradox raises interesting questions about knowledge and expectations. It shows how our attempts to outsmart or predict something can sometimes create the exact outcome we're trying to avoid. The students' logic led them to believe that the exam would never happen, but it was that very reasoning that allowed the surprise to occur. This paradox is often discussed in the context of self-referential statements, where reasoning about the future leads to an unexpected result. It highlights the complexity of trying to predict events in a world full of surprises. The preface paradox. Imagine an author who writes a book. Each chapter contains statements that the author believes to be true. The book is well researched, and the author is confident in the accuracy of every fact presented in each individual chapter. However, despite this, the author also believes that at least one statement in the entire book must be false. This seems contradictory at first. If the author believes that every statement in the book is true, why would they also believe that one of those statements must be false? Here's how it works. The author is aware that no matter how careful they are, there is always a possibility that one detail, one fact, or one piece of information could be wrong. It could be an oversight, an error in data, or a misunderstanding. Because of this, the author acknowledges that, although they believe all the statements in the chapters to be true, there must be at least one mistake somewhere in the book. Now, consider the paradoxical nature of the situation. In each chapter, the author's confidence in the truth of the statement seems absolute. But on a larger scale, the author knows that they cannot be infallible. The paradox arises because the author simultaneously holds two beliefs that seem to contradict each other. They believe every individual statement in the book is true, but they also believe that, as a whole, one of the statements must be false. This is the essence of the preface paradox. It forces us to think about how we balance certainty and uncertainty. It highlights a strange tension between believing in the truth of individual statements and accepting the possibility of error in the whole. The preface paradox is similar to other paradoxes that deal with self-reference, where our logic about individual pieces doesn't always match up with the larger whole. It's like saying, every chapter in this book is true, but somewhere in this book there is an error. In a sense, the author is both confident and uncertain at the same time. In the real world, this paradox is relevant when we think about knowledge, truth, and human limitations. How often do we confidently hold certain beliefs, but also acknowledge that despite our confidence we might be wrong? This paradox mirrors how we live in the tension between certainty and doubt. The paradox of the unexpected choice. Imagine a person who always makes decisions that they believe are in their best interest. Every time they choose, they feel confident that their decision will lead to the best possible outcome for them. Yet, despite always trying to act in their best interest, they sometimes find themselves surprised by the results. At first glance, it seems logical. If you make a choice that you believe is best for you, why would the outcome be surprising? If you choose something because you think it's the right decision, it should align with your expectations. But that's where the paradox begins. The paradox arises from the tension between certainty of choice and unexpected results. The individual makes a decision with full knowledge and confidence that it is the optimal one. But even with this confidence, the outcome still defies expectations. This paradox challenges the idea that perfect reasoning always leads to expected results. It shows that even with the best decision-making skills, human judgment can sometimes lead to surprising, unintended consequences. One reason for this is that there are so many factors beyond our control. Unpredictable events, other people's actions, or changing circumstances that can influence the outcome. Even though a choice may seem like the right one at the time, these external factors can alter the result in ways that surprise us. Consider the example of choosing a career path. Someone might decide to pursue a specific job, believing it will bring fulfillment and success. But despite their careful planning and reasoning, they might find that the job doesn't offer the satisfaction they expected. The unexpected outcome isn't because the decision was wrong, but because other factors, such as workplace culture or unforeseen personal challenges, shape the result in ways they could not predict. The paradox also reflects the limits of human understanding. Even when we think we know the best course of action, the complexity of life often introduces surprises. It's a reminder that no matter how much we control our decisions, we can never fully control the outcomes. The paradox of the unexpected choice invites us to think about our assumptions. If we make a decision that we believe is ideal, how can we be so sure of its outcome? The paradox suggests that even with the best intentions and reasoning, life has a way of surprising us. The paradox of the unexpected result. Imagine you've planned something carefully, taking into account every possible detail. Every variable has been considered, and every scenario has been thought through. You've prepared for every contingency, and you're confident that the outcome will unfold exactly as expected. And yet, despite your best efforts, something goes wrong. The plan doesn't work the way you thought it would. A completely unexpected result occurs, something you could not have predicted. This is the paradox of the unexpected result. It occurs when everything seems to be in place, when all the information and all the preparation suggest a certain outcome. And yet, despite all this, the result defies your expectations. At first, this seems like a failure of planning or reasoning. If you accounted for everything, why didn't things go according to plan? But the paradox is deeper than that. It highlights the limits of prediction. Even with the best planning, we can never fully account for every variable or unforeseen event. There are always unknown factors, those small, hidden details or external influences that can shift the outcome. Consider a business launch. You've done market research, studied trends, and crafted a well-thought-out strategy. You're ready for success. Yet, when the product is released, the response is underwhelming. Despite all your careful preparation, the outcome was unexpected. Or think of a scientific experiment. You've designed the experiment meticulously, accounted for every variable, and expected a certain result. But when you run the experiment, the results are not what you anticipated. The experiment works, but not in the way you expected. Something about the variables, the conditions, or the unexpected behavior of the system led to a surprising outcome. This paradox is a reminder that even when we think we understand all the variables and factors at play, the universe is far more complex than we can predict. Every plan, no matter how thorough, is subject to the unpredictability of the world around us. It also speaks to the inherent uncertainty in all human endeavors. We can try to control everything, to manage all risks, but the outcome remains unpredictable. Sometimes the unexpected result is not a failure, but simply a reminder of the complexity of life. The paradox of the unexpected result forces us to acknowledge that there will always be things beyond our control. No matter how prepared we are, the world can surprise us. It encourages us to be flexible, adaptable, and ready for the unknown. The paradox of the time traveler's memory. Imagine a time traveler who goes back in time, aiming to change something significant. Perhaps they want to prevent an event from happening, or they intend to alter the course of history in some way. They successfully change the past, and the timeline shifts. Now, here's the paradox. If the time traveler's actions have changed the past, how can they remember what happened in the original timeline? If the event they changed no longer occurred, then the memories tied to that event should no longer exist in their mind. For example, imagine the time traveler goes back and prevents an accident that they were once involved in. If the accident never happens, the time traveler should never have been affected by it. So, how could they remember the event or even remember being involved in the accident at all? This creates a paradox. The time traveler has changed the past, which means the memories of their original experiences should have disappeared. But if their memories disappear, how can they continue to travel through time? How can they even recall why they made the changes in the first place? The paradox lies in the relationship between memory and time. If a person's memories are tied to a specific version of events and the events change, then their memories should also change or vanish entirely. Yet, if they can still recall their journey and actions, then their interference with the timeline would have no real effect on their memory. Some theorists argue that the mind might adapt to new timelines, and the time traveler would simply remember the events as they are in the altered timeline. In this case, the paradox resolves itself in the sense that memory is fluid and can change with reality. However, this still leaves the question: how does the mind handle the existence of conflicting memories from different timelines? This paradox raises deep questions about identity, consciousness, and the nature of time itself. If time can be rewritten, how do we as individuals retain our sense of self? Can we remember who we were in a timeline that no longer exists, or are we forever shaped by the current version of reality? The paradox of the time traveler's memory challenges our understanding of how memory, identity, and time intersect. It shows how altering the past could create a rupture in our personal histories, leaving us to wonder how much of what we remember is truly our own, and how much is simply the result of the timeline we inhabit. The paradox of the uncertainty of prediction. Imagine you are trying to predict the outcome of an event, say the weather, a sports game, or even the stock market. You analyze all available data, apply your knowledge, and come to a conclusion about what will happen. But here's the twist. The very act of making the prediction might change the outcome itself. This is the paradox of the uncertainty of prediction. It suggests that by predicting the future, we may be influencing it in ways that make the prediction less certain or even inaccurate. Take, for example, the stock market. If a large number of investors predict that a particular stock will rise in value, their collective actions might cause the stock to rise simply because they expected it to. This creates a feedback loop. The prediction becomes a self-fulfilling prophecy. But does that make the prediction more reliable, or is it now altered by the very people who are predicting it? Similarly, in sports, if millions of fans predict that a team will win, those predictions may influence the team's performance, the strategy of the coach, or even the attitude of the players. The prediction changes the environment, making it harder to determine what the real outcome might have been without those expectations. In scientific research, predictions can affect experiments. If scientists predict a certain outcome and are biased by those expectations, they may unintentionally skew their results to fit their predictions. This uncertainty can make it difficult to separate the prediction from the reality, challenging the integrity of the prediction itself. This paradox highlights the difficulty of making accurate predictions when the act of predicting is itself an influence on the event. In some cases, predictions seem to shape the future, rather than simply reflecting what is likely to happen. It also calls into question the very nature of knowledge and control. If our predictions are always changing the outcomes, how can we ever truly know what will happen? Can we predict anything with certainty, or is every prediction an interaction with an uncertain, ever-changing future? The paradox of the uncertainty of prediction suggests that the future is not something we can simply observe or measure. Instead, it's something we help to create with every prediction we make. It invites us to consider how our expectations shape the world around us, and whether the act of knowing changes the things we seek to know. The paradox of the ship's journey. Imagine a ship setting sail on a long journey across the ocean. As it travels, every part of the ship is slowly replaced. The wooden planks of the hull are swapped for new ones. The sails are replaced, and even the crew is gradually replaced over time. After months or years, the ship reaches its destination. But is it still the same ship that set out on its journey? At first, this question seems simple. Of course, it's still the same ship, right? It has the same name, the same purpose, and it's been sailing to the same destination. But as more and more parts of the ship are replaced, the question becomes less clear. If every single part of the ship is swapped for a new one, is it still the original ship? Or has it become something entirely different, merely a replica? This is a version of the ship of Theseus paradox, but here it focuses on the idea of gradual change over time. Each replacement happens one step at a time, with no single part being swapped that would immediately make the ship unrecognizable. But eventually, the ship has changed so completely that it raises the question, does continuity of function and identity still make it the same ship? This paradox forces us to think about what makes something truly the same over time. Is it the physical parts that matter, or is it the purpose and continuity of the ship's journey? Is a ship still the same if the essence of its purpose remains intact, but all of its components are different? This idea also applies to people. Over the course of a lifetime, people change physically, mentally, and emotionally. Cells in the body are replaced and memories shift. Are we still the same person we were years ago? At what point do we stop being who we were and start being someone new? The paradox of the ship's journey isn't just about ships or people, it's about the nature of identity and continuity. It asks us to reflect on what makes something the same as it undergoes gradual change. Is it the individual components, Or is it the larger idea of the ship, the person, or the journey that makes it whole? The paradox of the ravens. Imagine you make a statement, all ravens are black. You're confident in this statement because every raven you've seen so far has been black. Now you begin observing the world in search of evidence to support your statement. One day, you see a black raven. This seems like perfect confirmation of your hypothesis. It fits with what you already know, that all ravens are black. But here's the paradox. What if, instead of a raven, you observe something completely unrelated, a red apple, for instance? Does the red apple somehow support the statement that all ravens are black? Of course, this feels odd. The apple has no relevance to ravens, and yet, according to logic, the apple being red could actually be evidence in support of the statement. This is the paradox of the ravens, also known as Hempel's paradox. It shows that evidence for a universal statement like all ravens are black can come from an unexpected source, even if that source has no direct connection to the thing being studied. If you find a black raven, it strengthens the claim that all ravens are black. But if you see a red apple, it also seems to provide evidence. This happens because, in a formal logical sense, a red apple is an example of something that is not a raven and therefore doesn't contradict the statement. Essentially, when you see a non-raven object that is not black, it doesn't disprove that all ravens are black. In other words, anything that is not a raven and does not contradict the statement all ravens are black could be considered evidence in its favor. This paradox reveals something peculiar about the way we gather evidence. It shows that some forms of evidence seem to be more obvious than others, while other forms seem irrelevant or nonsensical. It raises the question of what truly constitutes useful evidence when we're trying to prove a universal claim. In practice, we would rarely consider a red apple as evidence for the blackness of ravens. But logically, it seems that the more you observe unrelated things that don't contradict your hypothesis, the more evidence you gather. It challenges how we think about confirmation, the way we gather evidence, and the nature of logical reasoning. The infinity paradox. Imagine you're standing at the edge of an infinitely long road. You can walk for as long as you want, but you'll never reach the end, because there is no end. Infinity is something that can never be fully reached or completed, yet it's something we can conceive of in both mathematics and the universe. Now, let's consider a strange question about infinity. If you subtract infinity from infinity, what remains? At first, this seems like a simple question. Surely, subtracting infinity from itself leaves zero, right? After all, if you have an infinite quantity and you take away the exact same infinite quantity, you should be left with nothing. But that's not what happens when you actually try to perform this operation in mathematics. In fact, subtracting infinity from infinity doesn't always result in zero. It leads to an undefined or indeterminate result. The reason is that infinity isn't a single fixed value. It's a concept that represents something without bounds. And when you try to subtract two infinite quantities, you end up with a situation that can't be easily resolved. The result depends on how those infinities are defined and how they relate to each other. Consider the example of two different infinities in mathematics, one representing the set of all whole numbers and another representing the set of all even numbers. Both of these sets are infinite, but they are not the same. If you subtract the set of even numbers from the set of all whole numbers, you still have an infinite number of numbers left. The idea of subtracting infinity depends on the type of infinity you're working with and how you define your set. This paradox highlights the strange properties of infinity. It's not something that behaves like regular numbers, where subtraction always follows a predictable rule. Infinity doesn't follow the usual rules of arithmetic, and that's what makes it so difficult to comprehend. It's a concept that can appear simple, yet the more we explore it, the more complex and counterintuitive it becomes. The infinity paradox also raises questions about the universe. If the universe is infinite, then can we ever fully understand it? If the universe has no end, does that mean that every journey, every discovery, and every experience is ultimately endless? In a way, the infinity paradox challenges our understanding of limits. It reminds us that not everything in life can be neatly wrapped up with a simple solution. Some things, like infinity, don't follow the rules we're accustomed to. The Banach-Tarski paradox. The Banach-Tarski paradox is one of the most mind-boggling concepts in mathematics, and it challenges our understanding of geometry, space, and even reality itself. The paradox is based on a seemingly impossible idea. It suggests that it is possible to take a solid sphere, cut it into a finite number of pieces, and then reassemble those pieces into two identical spheres, each the same size as the original. At first glance, this seems completely absurd. How could you take a single object, break it into pieces, and then create two objects that are exactly the same as the original, all without adding any new material? But this paradox is a result of certain mathematical principles, specifically the properties of infinite sets and the concept of non-measurable sets. To understand how this paradox works, let's break it down. In the world of standard geometry and physical objects, this process is impossible. If you cut a ball into pieces and tried to rearrange them, you would never end up with two perfect spheres. But the Banach-Tarski paradox exists in the realm of abstract mathematics, where things don't have to follow the same rules as real-world objects. The method relies on infinite sets and non-measurable sets, which are mathematical concepts that don't have well-defined volumes or sizes in the usual sense. These pieces, once divided, don't behave like regular chunks of matter. Instead, they have properties that allow them to be rearranged in impossible ways, almost like they exist in a space where the normal rules of physics and geometry don't apply. In simple terms, the Banach-Tarski paradox shows that, in the abstract mathematical world, you can make seemingly impossible things happen. The paradox uses infinite divisibility to manipulate shapes in ways that defy our intuition. By breaking the sphere into an infinite number of pieces that are too small to measure in the traditional sense, it's theoretically possible to reassemble those pieces into two perfect copies of the original. The implications of this paradox are both fascinating and unsettling. In reality, it's impossible to apply this process to physical objects, as it requires infinite precision and the handling of non-measurable sets, which don't exist in the real world. But it highlights the strange properties of infinite mathematics, where the rules we use to understand the world around us don't always apply. The Banach-Tarski paradox forces us to confront the limits of our understanding of space and geometry. It shows that infinity behaves in ways we can't always imagine. While it is a purely mathematical concept and doesn't apply to physical objects, it raises profound questions about the nature of reality and how we interpret the world.